We're going to look at the problem of getting two heads when we flip a fair coin twice to look at tree diagrams. So we could find this probability simply by listing the sample space. Heads, heads, tails, heads, heads, tails, 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 and see that one out of those four is heads twice. For a simple problem such as flipping a coin, that's not very involved. It's fairly straightforward and quick to list the sample space. But a lot of times it's not that simple. What we can do is we can create a tree diagram to help us organize our probabilities and our events. So we're going to use a set of branches to represent each event. So here's our first event. This is event 1. And we're looking at, is the coin going to be heads or is it going to be tails? And then we have a second event. So we make another set of branches coming from that first node, it's called. N-O-D-E, node. If this head is a node in the tree diagram. It's where a new event branches off of. And event 2 we're looking at, is it heads or is it tails? Is it heads or is it tails? And if we were doing something like rolling a die, we'd have 6 branches for one of these events labeled with 1, 2, 3, 4, 5, 6. From here we can see our sample space simply by following the branches of the tree. Head, 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 tail, tail, head, or tail, tail. And we can list our sample space from that. Okay, great. How does that help us with probability? A lot of times we'll label our branches with the probability of each event. So the probability of getting heads on the first flip is 1/2. The probability of getting tails on the first flip is 1/2. On to event number 2, the probability of getting heads is still 1/2. Getting heads on the first one doesn't affect heads on the second one. And same thing all the way down, 1/2, 1/2, 1/2, 1/2. And now we can simply multiply our branches together. Probability of getting head, head, that was 1/4. It's 1/2 times 1/2. Probability of heads, tails, 1/2 times 1/2, 1/4 again. And all 4 of these outcomes ends up being 1/4. So the probability of getting 2 heads, 1/4. The probability of getting no heads, 1/4. And the probability of getting one of each, well, that's both of these things. That's head, tails, or tails, head. We add them together, we have 1/2. So there's the basics of a tree diagram. We'll see it a little bit more right here. This one's not quite as straightforward. We have a class, we have left-handed people, right-handed people, males and females. Suppose that we choose 2 students at random, draw a tree diagram that shows the sample space, and find the probability that both students are left-handed. So what we care about is whether or not the student is left-handed or right-handed. So in our tree diagram, event 1 is picking a student, and we're looking at, are they left-handed or not left-handed? Complement of being left-handed. And then a second pick, we look again, is the student left-handed or not left-handed? Now we label the probabilities. So on the first pick, what is the probability that we pick a lefty? Well, it is 4 out of a total of 28 students. And the probability of picking a right-handed person, a person that's not left-handed, that would be 24 out of 28. We can total up here. Lefties is 4 and 28. Those are the numbers we care about. There's a total of 28. Sorry, this should be 24. Now, when we pick 2 students, we're not going to pick the same student twice. So these 2 events, picking first student, picking second student, those 2 events are not independent. They're conditional. So picking this student we already know that a lefty got picked. How does the probability change? Well, now there's only 27 students in the class that we have to choose from, and only 3 of them are left-handed. This would be the probability of picking a lefty given that we know a lefty was chosen. What's the probability of not picking a lefty? Well, there's still 24 non-lefties out of the 27 kids total that we have left to choose from. So this would be the probability of not a lefty given that a lefty was chosen. Notice that the pairs of branches total 1, and that should always happen. Try to fill in the bottom 2 branches. What is the probability of picking a lefty given that we didn't pick a lefty? That's going to go right here. And what's the probability of picking a non-lefty given that we picked a non-lefty first? That's going to go right there. Well, if we picked a right-handed person, that means that there are 4 lefties out of 27 still there. And if we picked a righty, now we only have 23 righties out of the 27 total. So what is the probability of getting 2 lefties? We follow the branches for left-left. We go that way. That branch is considered to be a success for us. So we're going to do 4 out of 28 times 3 out of 27. This probability is approximately 0.016. So this tree diagram allows us to see all of the possible things that can happen, and we can find the probabilities by following the branch for what we are finding the probability of. And that leads us to our general multiplication rule. The probability that A and B both occur can be found by using this rule. Probability of A and B, A intersect B, is the probability of A times the probability of B given that A occurred. That's what we just did with that tree diagram, where B given A is the conditional probability that B occurs given A already occurred. And there we go. That should be the tools that you need to get you rolling on your practice problems.